All right, today we're looking at the circle geometry in grade 12, and specifically we're going to look at all the theorems that relate to circles, and then you'll be able to solve problems once you know the theorems. Okay, first of all, the things you should know when you're talking about circles is the different terms that we use. So we got a circumference. I'll just put them down there so you can see them. Circumference, what is a chord, secant, a tangent, radius, diameter. So circumference is the line that makes up the circle. A chord is a line that touches the circle, that goes through, but it touches the ends of the circle but doesn't go through. A secant cuts through the circle, as opposed to a chord. A tangent touches. Then you have a radius, which is from the center of the circle to the circumference. And you have the diameter, which is, where is it? That's the diameter there, sorry. And then that was the tangent. Okay, so those are the things that make up the circle. Right, now the first theorem that you come across in circle geometry is the one that says that a line that joins the center of a circle to the midpoint of a chord will be perpendicular to that chord. Okay, so what you've got is a circle and a chord. Now if you take a line from the center of the circle to the midpoint of the chord, right, like that, so there's the center. That's the midpoint of the chord. In other words, that piece there is equal to that piece there. It will be perpendicular to the chord. In other words, it will form a right angle, like that. So that's the first theorem. Okay, all the ways to prove it are in your textbook. You will be expected to know 2 or 3 of them for the exams. The converse of this theorem says that if you draw a line from the center of the circle in such a way that it is perpendicular to that chord, it will cut the chord in half. Okay, so that's the converse. This one says that you first of all have it bisecting, then it's perpendicular. This one says if it's perpendicular, it will bisect. That's the first theorem. The second one, now the word subtends you haven't maybe heard of, but basically an angle stands on an arc or a chord. Okay, so there is an arc, this angle stands on it. So that's what subtends means. Okay, so if an angle subtends a chord at the center, it will be twice the size of the angle that is subtended by the same chord or arc on the circle. In other words, this angle here is twice this one here. So if this one was 180, that one would be 90. That's the second theorem. Okay, it's quite handy because it brings us to the third theorem, which is that an angle subtended by the diameter. Now a diameter goes through the center, but it's also a chord. Okay, so the theorem over here said that if it's subtended by a chord at the center, it will be twice the angle at the circumference. So this one says that if you've got the diameter and you draw an angle like that, it forms a 90-degree angle there. Why? Because this is 180 degrees subtended by this arc. So that angle there, subtended by the same arc, is half. Okay, so that's the third theorem. Very handy, especially for analytical geometry and problems that we're going to get closer to the time. Angles subtended by an arc or a chord on the same side of the chord are equal. Okay, now this is what a lot of teachers call the bow tie theorem. Okay, there's your bow tie. The trick is that all 4 corners, all 4 angles must touch the circle. Okay, so this arc here subtends that angle. The same arc subtends that angle. So those 2 angles are equal. Similarly, this arc here subtends that angle there, and it also subtends that angle there, so those two angles are equal. Okay, so if you look for bow ties in your problems, you'll always find angles that are equal. Trick, they must touch the circle. Okay. Right, now that brings us to what we call a cyclic quadrilateral. What's a cyclic quadrilateral? It's a quadrilateral, four-sided figure that all four corners are on a circle. Okay, now what this theorem says is that this angle here and this angle here will add up to 180 degrees. The proof for that, as I say, is in your textbook, but just quickly, what you will do is you will have the center, okay, pretend that's the center, it's actually there, okay? This angle here is double this one, okay? Similarly, this angle here is double that one. All these angles add up to 360, so those must add up to 180. So supplementary adds up to 180. All right. Brings us to the next cyclic quadrilateral theorem, which is actually the easiest one of the lot, and that is the exterior angle is equal to the interior opposite angle. Not like a triangle, where you've got the exterior angle equals the sum of the opposite angles. Okay? For a cyclic quad, it's only the opposite angle there. Okay? It mustn't touch the two lines that make up that angle. It's always opposite. All right. Now we get to the tangent theorems. Okay, the first one, you can think of an ice cream cone if you like, dunce's hat. All right, it says that if you draw a tangent from one point and another one from the same point, then these two lines are equal in length. All right, now how that works, if you want to prove it, you've got the center, so you'll draw a line to there, you'll draw a line to there and a line to there. Now, there's a theorem we're going to do that says that that angle is 90, so that one is also 90. This is a common side, so these two triangles are congruent. Therefore, those two sides must be equal. Okay. Easy theorem to prove. Okay, a radius is perpendicular to the tangent and the point of contact, was just what I mentioned. If you've got a radius drawn to a tangent where it touches, that angle formed, 90 degrees. Right, it's very easy. In analytical geometry, it's used a lot. Okay, but there they use gradients, because the gradients multiplied by one another must give you -1. So that is that theorem in analytical, but it's also used in circle geometry as well. Right, the next theorem and the last theorem for circles and tangents is if you've got a circle and you have a tangent drawn, where the tangent touches the circle, if you've got a chord that is formed, that angle that's there will be equal to the angle that is subtended by this chord. In other words, this is here is equal to that one there. Okay. Now, as I say, we've given some of the theorems names. We had the bow tie theorem. There was that one with a dunce's cap or ice cream cone. This one looks like a windsurfer. Okay, there's the board, there's the sail, and there's the sun in the background. Okay, so if you look for that, you'll find it. So similarly, this angle here will be equal to that one there. Okay, tangent, chord, angle, alternate segment, subtended by that chord. It must be from the endpoints of that chord going and touching the circle. Otherwise, it doesn't work. All right, so those are the theorems that you have to know. As I say, you will be asked one or two of them. There's 6 or 7 marks each, giveaway marks. Okay, if you don't know how to prove them, you're going to lose those marks. And for every few marks you lose, and you could end up losing a symbol. Okay, now we need to know how to use those theorems. The trick when you are solving these riders, geometry problems, okay, is you've got to know your theorems. You can't not know what's going on and then go and prove the theorem, the riders. So if you know your theorems backwards, you'll be able to do the problems. Use colored pens and or pencils, okay? And then before you even look at the questions, look what's given. Before you look at the questions, go and find things that are equal. that you know, because of your theorems, you know that's the case. And then go and see what the question says, and maybe you've already answered it just by looking at things that are equal. Okay, so yeah, is a problem. And everybody goes, how can we do that? Okay, it's just disgusting, all these lines all over the place. So one thing that we have to look at is what is given. They tell you there's a diameter. The diameter should give you a little alarm bell going. What do you know about the diameter? Angle at the center at the circumference is 90 degrees. You've got a tangent. What does that mean? Okay, and you've got the word perpendicular. What does that mean? They're telling you that DC is perpendicular to AC. Okay, so we've got DC. There it is there, perpendicular to AC. So what do you know about angle C1 and 2? They add up to 90 degrees. Okay, so that's given, so you mark it down. What else have you been told? There's a diameter. Okay, now have a look. Does that diameter touch, have an angle touching the circle? Yes, it does. So what do you know about E3? Because of the theorem, it's also 90. Okay, I'll just move it. So now the whole thing moves. Okay, and that one there is 90. Okay, so we've got those two angles equal to 90. We've got a tangent to a circle. Now check if there's a windsurfer. There's the tangent. There's a sail. There's the circle. Okay, so what do we know about angle E2? It's equal to angle A. All right, so mark there. I use a right angle. Okay, so now E2, this one here, equal to that one there. Right, I'll move that now. Yeah, there it is. Okay, so that's equal to that. Okay, I haven't looked at any questions yet. I've just been marking off things that are equal. All right, and ABC tangent. Okay, obviously E4 will be equal to B1 as well, if you want to use that. And remember that all your your geometry stuff from a few years ago still applies. So vertically opposite angles, they're equal. Okay. So as you can see, I've used in colors, and you can mark them off. Right, let's see what the first question is. Prove that BEDC is a cyclic quadrilateral. Now, to prove a cyclic quadrilateral, you need to either find exterior angle equal to interior opposite, or angles in the same segment. Because if the angles are in the same segment, that means they lie in the circle. Right. I've already marked off that E3 is 90. What angle is that there? That's the interior opposite angle to that angle there. Can you see that it's already 90? So that is equal to that. Therefore, this must be cyclic because the exterior angle equals the interior opposite. Okay, so there's the proof. As easy as that. So you would write angle E3 equals 90 degrees. Angle in semicircle. You must give your reasons. Also, angle C is equal to 90 degrees. Why? It was given over there, perpendicular, right? Therefore, angle E3 must equal angle C, which is obvious. Okay. Therefore, BEDC is cyclic. Why? Because the exterior angle is equal to the interior opposite angle. Okay, proved. That was the first one done. Second one, prove that angle D1, look for it, D1 is equal to angle A. Okay? So in other words, if I can make that a little red dot, then that's equal to that there. Okay, now what have you just proved? You've just proved that this is a cyclic quad. Okay, so if you could, you would draw a circle where that would touch. Okay, there it is there. All four corners touch the circle. Okay, so we've got a circle. You don't have to go and draw it, but it does help to see it. Okay, now what do you know about a circle and angles in the same segment? They are equal. So there's my bow tie. Can you see it? Okay, so what do I know about E2? It's equal to D1. Have I proved my question? 2 red dots, that's done. Remember in geometry, if two things are equal to the same thing, they're equal to each other. Right, so you've got D1 is equal to A because they're both equal to B2. So how do you write it? You're going to say angle E2 is equal to angle D1. Why? Because they are angles in the same segment. Right? They're in the same segment because you've proved in the earlier question that BEDC was cyclic. Also, we know that E2 is equal to A. Why? We marked it off earlier because that's the tangent, there's the chord, there's the angle between the tangent and the chord equal to the alternate segment. So all you have to write here is tan chord theorem. So therefore, D1 equals A. That's all you have to write. Okay, last question. No, second last question. We've done that one. Right, now prove that CE equals CD. Now when you want to prove that CE equals CD, you have to prove that this triangle is isosceles. That's the only way you can, because it's two lines of a triangle, the only way you can do that is to prove that you've got an isosceles triangle. In other words, you've got to show that angle D1 and 2 is also a green line. Okay, just by looking at it, you can probably see that it is the case, okay, because B4 equals B1, sorry, E4 equals B1, tan chord theorem. E4 equals E1, vertically opposite angles. B1 is equal to D1 and 2. Why? Because that's the exterior angle of a cyclic quad equal to interior opposite. Therefore, D1 and 2 must be equal to B1. Okay, so it sounds complicated, okay, but once again, you're showing things are equal to the same thing. So you remember, make your argument logical so that it's not all over the place and then you're not just writing everything down that you think is the case and say, therefore, it's true. Okay, you've got to actually make an argument of what's going on. So, first of all, E4 is equal to E1 because they are vertically opposite angles. E4 is also equal to B1 because it's the tan chord theorem. B1 is equal to D1 and 2. So we can call it angle D because there's no other angles around D, so it's D. We can say angle D. Why? Because it's the exterior angle equal to interior opposite. Exterior angle equals interior opposite angle. So therefore, E1 equals D. Therefore, CE equals CD. CE equals CD. Why? Because they are sides opposite equal angles. Now, notice over there, I used the word, the symbol equals, and over there I had to use the word equals. Okay. This was something on the left-hand side equal to something on the right-hand side, and that statement is true. If I use the word the sign equal here, if I wrote sides opposite equal angles, that statement doesn't make sense because how can sides equal angles? All right, so you've got to, your statement must still make sense. It can't be rubbish. All right. Okay, so this is the isosceles theorem converse. Okay, the sides are opposite equal angles, therefore they are equal to each other. Right, one more question. And let's prove that now we've got, this is also green from there to there. Okay, prove that B1 equals B3. B1 equals B3. Okay, it's going to, if you just look at it here, this is a cyclic quadrilateral over there. Okay, there's the bow tie. Now, just because we looked at it like that, there and there equal, or there and there equal, it doesn't mean that those two angles aren't equal to each other as well. So E1 equals B3. So if you then got to prove that E1 equals B3, you've already proved that this is cyclic. I've drawn the circle around it to show it. This B3 equals E1 because they are angles in the same segment. So you've got E1 equal to B1, proved earlier. Okay, somewhere I wrote it down. Well, you can see that it is. And B1 equal to B3, therefore B3 and B1 must be equal to each other. Angle E1 equals B1, proved. And angle E1 equals B3, angles in same segment. Therefore, those two things are the same, so those two things must be the same. B1 equals B3. Done. Right, so there's one problem where a whole bunch of theorems were used. Some things from previous years that you have to know that are taken for granted, like vertically opposite angles. Okay, perpendicular lines, they mean something. Okay, there's a right angle triangle, you might have needed it. Your tangent theorems were used, angles in the same segment, cyclic quad, exterior angle equals interior opposite. Okay, right, now you need to do exercise 12.1, number 3.